Hi, now welcome to another video lecture for vibration waves. We talked about resonance for two different properties: amplitude of a harmonic oscillator. A harmonic oscillator moves along x-axis is amplitude, and also the power of the driving force. We talked about the resonance of that property as well. So we have experience with resonance studying two different properties. The book has resonance of amplitude of the elastic amplitude and the absorptive amplitude that I would like you to study from the book. Okay, now I want to talk about a coupled system that is being driven by a force. So you can have many coupled systems. A simple one is like this: two pendula, equal length, equal mass. Now they are coupled by a spring, and so it's with a spring constant K. So this coupling is coupled the motions of A and B. We can also we can ignore the friction for a while. So if you write the equation of motion for the coupled system with an additional force, right? So with an additional force, this is the driving force that acts only on A. So this is preparation for when we study wave generation. So you can have a long string and the force driving motor or force, whatever, it's swinging the string up and down, like or waving the string left and right, so there's some mechanism where one end will be driving the motion. So here we have two, very simple system, just two masses. We had one mass and we learned that. Now we have two masses and we're going to drive them, but just acting on one of them. It's important to have this simple case, okay? You can, if you like, you want to study force on this and on that, that's another problem, but we can just study this. When you write out the equation of motion of this, you're going to go for the acceleration of A. You're going to get the same thing as coupled thing. This is the same old problem. So if I were to say this much is same, except I put the damping out here. So this is like the same undamped case we've done before. Wow, this thing doesn't have ink. So I'm gonna get rid of that. Get another one. So this part is same as before. This plus here, okay. And so this is same as before, and then we have driving force on A only, not on B. We're going to talk about the damping part in just a minute. So we know how, if I just had that problem, when you solve it, you get a because of symmetry, you have XA plus XB and XAX minus XB. If you didn't have a symmetry, there will be some B over A here and B over A here. So Q1 is this and Q2 is, these are the normal coordinates, and their frequencies are omega 1 and omega 2. You remember that, right? Okay. I don't want to deal with this coupled system, right? So these two equations 1 and 2, it will be nice to decouple them so that equation looks like equation of one S oscillator. And you would think this is different than the original problem, so they'll all have some common problem, right? It turns out no, it's really a miracle that happens if you take a double dot here, and plug in here and discover what second derivative of Q1 is, which is, this is same as before, right? So if these are the normal coordinates, I'm going to get separate harmonic oscillators. In addition, what I get for Q1 is an equation that's a driven oscillator. For now, just ignore this, the damp part. I get driven oscillator Q1, and Q2 also is driven oscillator, but it's a single oscillator. And single oscillator driven, we already studied that. So it's kind of pretty cool. I think it's you can appreciate that I can't solve that problem. But instead of solving that problem, I'm going to change variable. So it's basically change variable. So if I go from this set, change variable, you might say change variable. A normal mode technique that we learned actually tells me what variable to change to. That's awesome actually. Normal coordinates are awesome things, okay? So once I change variables to normal coordinates, and I have a problem which I already know. I have already solved these separate problems. Problems like these, I have solved them. This is like a oscillator, which I'm going to call Q1, is being driven by this. So let me go back here and introduce damping. If A was maybe damped, was moving in something liquid and it was damped, B was damped, A was damped and B was damped, and they were kind of sloshing around in the liquid, then I would get a damp, for instance, air. Just air will damp it, right? So air will hit A and B, air particles and damp it. So you'll have a damped A and damped B. Now when you change the variable to Q1 and Q2, you don't mix up Q1 and Q2. You get Q1 damped driven oscillator, Q2 damped driven oscillator. So I can go ahead and write the most general solution I can think of writing about these guys. Well, that's going to be a very complicated solution, damped driven oscillator. So I'm going to do a simplification. We can say, hey, you know what? I want to study steady state. So I'm going to look at T much greater than 2 over gamma. So when if there is no damping, then gamma will be 0, and I won't really run. This will be a crazy thing. If gamma is 0, T much greater than infinity. What do I mean? Well, that's why I want to keep gamma around. Okay, so gamma actually helps us understand some of the things away from the things becomes infinite and a little crazy. So it's best to study it in a damped system. Even if you don't have damping, then the ideal system has a little bit of mathematical problem here and there. Okay, so you have to handle it more carefully. Here we can, with the damping, we can just carry forward with our understanding of damped driven oscillator, and we don't have to deal with this infinities arising here and there. Okay, so in the steady state condition, Q1 looks like, I can write elastic and absorptive, but I can write also amplitude and phase lag. I can write amplitude and phase lag for this guy, and I can write a common formula for both of them. So this is where the 0 used to be. So it's like omega 1 2 squared is here, and then I have a minus omega square, which is the driving frequency of the driver, and gamma, which is exactly like it used to be. Okay, and I know I had a formula problem here. Square root. It's not square root. This is correct. Okay, so the phase lag for 1 or 2 is depends on frequency 1 or frequency 2 you use. All right, so I want to, this is the solution. If you want to say, hey, I am interested in not Q1 and Q2, but I am interested in XA and XB. Of course, you can just add it, divide by 2, get XA. Subtract it, divide by 2, get XB. Right? So I want to know power. So let's look at the powers. In the end, I want a power. So this is instantaneous power. So I have a force F0 acting on A. So force F0 cosine omega t dxa dt. So this is the instantaneous power. So xa is basically q1 over q2 divided by 2. So this is going to be half f0 cosine omega t. The velocity that goes with q1 over dt dq2 over dt. So far so good. So when I go in there, I remember this one, I can do it elastic. This will generate cosine and sine terms. So this will generate some a1 cosine omega t plus b1 sine omega t, and this will similarly generate a2 cosine omega, and these are omega 1. No, I'm sorry, this is not omega 1. This is steady state, so that's not omega 1. Omega 1 and omega 2 and inside the constants a's and b's. Okay, so this is going to be a1 b1 cosine omega t sine omega t a2 cosine omega t per b2 cosine sine omega t. So I'm going to have this generated, right? What is a1? I go out and take a derivative of cosine part, I get the sine. So that's going to be in b1. So this a1, the way I saw it is a1 omega sine delta 1. What's b1? b1 is, I take a derivative with omega, that makes it minus a1 omega cosine delta 1. So if similarly is formula for these, this will be similarly. So if a1 2 will be 1 or 2 b1 2 1 or 2 1 or 2. So that I've got all the formulas lined up. Now I see this cosine multiplied with cosine will give me cosine square. This cosine multiplied with sine will give me cosine sine. Over one period, it will go, if I average it, it will go to 0. So from here, I want to find time average, right? Sometimes we use symbol like this to say average. Or sometimes we write P average. So there are two symbols I can write for the average. A time average means I integrate over one period. So I go one period, and the period of this force is omega. So I could go 2 pi over omega. That will be one period, and 0 to t, 2 pi over omega, and I take P of t dt. After I integrate it, you would not be surprised that this is going to be a nasty looking thing, but these kind of terms will give me 0. This with that will give me 0, and this with that will give me 0. So the only one that remain will cosine squares terms. And let me make sure I can write them. So erase. I'm gonna have to get some room here. I don't have a whole bunch of space here to write. So let's erase all of this because there's nothing that we need from here. So erase this. So power, when you work this out, so average power should look like average power will look like 1 over 2 f0, and then I'm going to go with the thing that gets me a1, because that's the one which goes cosine. So f0, and I have a1, and cosine with cosine squared gives me half after averaging, and then this one goes to a2 plus a2 times half. So I got something from first oscillator, not oscillator, this is normal mode 1, and the other one gives me normal mode 2. So it kind of separates out. There is a power in normal mode 1 and there's a power in normal mode 2. Okay, so this is, turns out f0 is square over 4m gamma, and so this will be as if, let's call it contribution 1, so that would be gamma square omega square over omega 1 square minus omega square plus gamma square omega square. So that's this term a1, and the other one is gamma square omega square, and that's the only place that you have 1, omega 2 square minus omega square plus gamma square omega square. Okay, we know that this guy alone, if you just plot this guy versus omega, then you 0 and then at omega 1, and the width is whatever is here, is gamma. So the width is gamma, and this is the first term. Right? So, and if it's the second term, when you contribute this term, this is at omega 2, and this is, because of this is, they have the same damping, so this is gamma. So we get peaks at two different places where the normal modes are. These are normal mode frequencies. When you put them together to plot power, so this is omega 1 and this is omega 2. So remember that each omega is one experiment, right? You're driving at one frequency. You have a system, and you are driving at f0 cosine omega t. So you pick an omega, so you do one of these experiments, and then you have one point here. So you're going to get points like but then these guys start to add here, and it's going to be so you're going to get peaks wherever the normal modes are. So you can see I can actually find out normal mode frequencies by doing this driving frequency driven also. I can drive one of the masses, and my experiment will pick up these normal mode frequencies of the system. Pretty cool, I think. This experiment actually works. I wish we had the lab to show it to you. And when you see it, is pretty cool. The difference between this modeling and reality is that different modes, get damped different amount because they couple to whatever is damping mechanism a little bit differently. And so what will happen is, in reality, you will get the normal modes. So like you get the normal modes correctly, same place, but they may be like peaked like this, something like that, you know. They may be different in terms of gamma. Sometimes some of the normal modes may be suppressed so much. They may be so maybe this is okay, but this guy is not that way. But it just barely you can see it. So if you have seen spectroscopy and other kind of spectra, they basically are showing these resonance curves for power. All right. So I'm going to stop with that. I hope you study this. This is a very important section in the book, and we will see you in another video. Okay, bye.